In this video, we're going to be going through the medium questions on the Young modulus. Question 1a, we've got an elastic cord of 180 millimeters with this cross-sectional area, and we've got a spring constant as well. And this is the final length we're going to stretch it to. We know it's Hooke's law, and we've got to calculate stress in megapascal. So first of all, the equation for stress is force divided by area. But if you're having a look here, we haven't actually got a force, so we're going to need to work out the force from what we've got available. The equation we're going to use for force, because it obeys Hooke's law, and it says in the question, is K times delta L, where K is our spring constant. So our spring constant is 120 Newton meters. Our delta L we've got to work out, so that's our extension. So we're going to do 230, take away 180, so it's going to be 50 millimeters. And if we convert that into meters, it's 50 times 10 to the negative 3 meters. With that, then we can calculate our force, 120 times by 50 times 10 to the negative 3 meters, which gives us 6 newtons. And then we can put that back into our stress calculation. So we've got 6 newtons divided by the area it's given us, which is in millimeters squared. So we're going to need to convert that into meters. So this is times 10 to the negative 3 would be for just a millimeter, but it's a millimeter squared, so we would square that. So it's actually going to be times 10 to the negative 6 that we're timesing our 0.51 by. And what that gives us when we type it into our calculators is 11.76 times 10 to the 6 pascals. It asks for our answer in megapascals, so that's 12 megapascals. Two significant figures. The next question wants us to calculate the strain of the cord. So strain is delta L, or the extension, divided by the original length. So we've got our delta L, 50 times 10 to the negative 3, that's how much it extended by, and our original length was 180 times 10 to the negative 3. The times 10 to the negative 3's cancel out, and we get 0.28 to two significant figures. There's no unit because for strain, there's no unit. We're doing millimeters divided by millimeters or meters divided by meters, so the unit cancels out. And to calculate the Young's modulus, we do stress divided by strain, so we're going to use both the answers that we've already got. So 11.76 times 10 to the power of 6 pascals divided by 0.28, that gives us 4.2 times 10 to the power of 7 pascals. We've got the same unit as we did for stress because there's no unit for strain. Question 1d is asking us to explain quantitatively, so that means with numbers, how the Young's modulus of the cord would change if the diameter was twice as large, and assume the cord has a circular cross-section. So I've broken it down into 3 sections. First of all, we're going to be looking at our area. So the area of a circular cross-section is pi r squared. If we double our diameter, the radius will also double, and that means the area of our circle will increase by 2 to the power of 2. The first 2 is because we're doubling it, the power 2 is because it's r squared, and 2 squared is 4. So that means our area will increase by a factor of 4 if we double the diameter. Then we'll link it to stress, so our equation for stress is force divided by area. That means stress is inversely proportional to area. So if we make the area 4 times bigger, the stress will decrease by a factor of 4. It will be 4 times smaller. Then we'll look at our Young's modulus finally. So the Young's modulus is stress divided by strain. So Young's modulus is proportional to the stress, directly proportional to the stress. Therefore, it will also decrease by a factor of 4, just like the stress. So because we've made our cord double as wide, we've doubled the diameter, the Young's modulus will decrease by a factor of 4. Question 2 shows a tower crane with 3 identical steel cables. The length of each cable is 41 meters. And we've got a braking force of 2.7 meganewtons. So we just write out 2.7 times 10 to the power of 6 newtons. That's what mega means. And we're working out just one cable, and we've got the radius as well, which if we convert into meters is 12 times 10 to the negative 3 meters. First thing we want to consider is that the braking force we've been given is for all 3 cables. So if we work out for 1, we would do this divided by 3. So the force in each cable is 9 times 10 to the power of 5 newtons. We are going to be working out stress. So the equation for stress is force divided by area. We've got the force, we just need to work out the area as well. And I'll put it all in the equation together. So stress is equal to our force, 9 times 10 to the power of 5, divided by our area, which is pi times r squared. Don't forget, it's in millimetres. So we'll put r squared outside of the bracket, including our times 10 to the negative 3. And then if we were to type that all into our calculator, we should get 1.989 times 10 to the 9 pascals, which if we round it to 2 significant figures, our stress is equal to 2.0 gigapascals. That's what times 10 to the 9 is. Question 2b. When the crane supports a load, each cable has a force of 500 megapascal and they obey Hooke's law. Calculate the mass of the load. So let's write down what we know first. We've got our stress from the question, 500 megapascals, which is 500 times 10 to the 6. And we worked out the area in our last question, which was pi times 12 times 10 to the negative 3, and we squared all of this. So that gave us 4.52 times 10 to the negative 4 meters squared. Then we need to think, what else do we know? So if we have a think about what's going on here, we've got our weight pushing down, and then we've got 3 cords holding it up. So if it's each worth T, we've got 3 lots of tension there pulling up. So if we're thinking about equilibrium, whatever the force of our tension in our wires times 3 is going to be equal to our weight of the masses going down, and we're calculating the masses going down. So what we do know, or we can work out, is what this value 3T is going to be, or at least what 1T would be. So the force in each of those wires is going to be equal to the stress times the area. I've rearranged that from stress is equal to force divided by area. That's where that came from. So what I can do is if I do the force times the area, so 500 times 10 to the 6 times by 4.52 times 10 to the power of negative 4, I get 226,000 newtons. And that would be the force provided by each cable to balance out this mass. And so we've got to times that by 3, which is 678,000 newtons. So that's our overall force going up, and therefore our overall force going down. And that weight is equal to mass times gravity. So all I need to do now, remember weight is mass times gravity. So the mass is going to be the weight divided by gravity. We're going to do 678,000 divided by our value for gravity. So if we type that into our calculator, our mass is equal to roughly, and I have rounded it to 2 significant figures, 69,000 kilograms. Question 2c. The unstrengthened of the cable is 41 meters. Calculate the final length of each cable when supporting the load and give your answer to 3 significant figures, and it's given us a Young's modulus as well. So I'm going to write down our Young's modulus expression first of all, but we can expand this out because we know what stress is, force divided by area, and we know what the strain is, which is delta L divided by L, but we're dividing by the strain, so we flip it over, and we tend to write an E here instead of delta L, E for extension. And we're going to rearrange this so we can get the extension, or delta L. So we're going to rearrange to get E is equal to FL divided by capital E, A. So our extension is equal to the force times the length divided by the Young's modulus times the cross-sectional area. And then we simply need to put in our numbers. So our extension is first the force, which we're going to take from earlier on in each wire, 226,000, and we're going to times it by the original length, which is 41 meters, and then we're going to divide it by the Young's modulus it's given us, 2.1 times 10 to the power of 11, and then finally we times that by the cross-sectional area, which again we worked out earlier, 4.52 0.52 times 10 to the negative 4, and that gives us a extension, or a delta L, of 0.09761 metres, but it did want the final length, so we're going to need to add that to 41. So we'll get 41.09761, which we could round up 41.1 metres. Question 2D wants us to calculate the combined stiffness constant K for all 3 cables and give a unit. So I've copied down from the previous questions what we already know and what we're going to need here. So we're going to be using the equation F equals K delta L and rearrange it for K. So we need the delta L, 0.09761, and then for the force, or the weight, we're going to use the total weight from part B. So before we divided it by 3, this is the weight of all, or the weight that the 3 cables are supporting, so the total weight of our masses. So we're going to do 6.78 times 10 to the 5 divided by 0.0761. And the answer that we should get for K is 6.95 times 10 to the power of 6. And it does say to give an appropriate unit, so it's going to be newtons per metre. And we can work that out because force is in newtons, and our delta L is going to be in metres, so it will be N/m, or Newton metre minus 1. Question 3A, we've got a steel wire with a ball which is then dropped. So the total length of the wire is 1.5, we've got the diameter of the wire, and we've got the mass. So I've written down all the information we have here. As the mass is released, it falls freely until the wire becomes taut. The gravitational potential energy is converted into elastic potential energy as the wire extends to maximum of 2 millimeters, and there's no other energy transfer. So I've written out all the information we have. First thing we can work out is the gravitational potential energy that the ball would have gained as it fell. So our equation for gravitational energy is mg and then the change in height. So the mass is going to be 32 grams. So we do need to convert that into kilograms because that's what we usually use to keep all of our units good. So that we times 10 to the negative 3. Times it by gravity, 9.81. And then for the height, we've got to think, first of all, it's going to fall the 1.5. But it's also going to fall this extra 2 millimeters. So it's actually going to be 1.502. We can just put that in there because it's 2 millimeters. So it's 2 times 10 to the negative 3. We could add these up separately if you're wondering where that came from. If we times that all together, we get the gravitational potential energy, GPE, is equal to 0.472 joules. So that's what it should have lost. That's what it would have had at the top for our potential energy, and that's what it's lost as it's fallen. Then we've got to think about its elastic potential energy, and our equation for that is half times the force times the change in length, which you do have on your formula sheet written slightly differently as W is equal to half F x, where x is our extension. It's the exact same equation that we're using here. So we're going to rearrange that for F. So F is going to be equal to our elastic potential energy times 2 divided by delta L. And it says in the question that all of that gravitational potential energy is converted into elastic potential energy. So we're going to use our answer from the one above, our GPE. So we do 2 times 0.472 divided by our extension, 2 times 10 to the negative 3, or 2 millimeters, and you should end up with a force of 472 newtons, or 470 if we're doing it to 2 significant figures. 3b is then calculating the stress. So our equation for stress is force divided by area. So we've already got the force, so that's easy. Our area, we're going to do pi d squared divided by 4. So what we need to type into our calculator is pi times 3 times 10 to the negative 3, all of that squared, divided by 4. So we'd calculate our area as 7.0686 times 10 to the negative 6 meters. And then we need to pop that into our stress calculation, where the force is going to be that 472 from the question above. So it's 472 divided by our 7.0686 times 10 to the power of negative 6. And that gives us an answer of 6.7 times 10 to the power of 7 pascals. 3C is asking us to calculate the strain. So that's going to be the change in length divided by the total length. So our change in length was 2 times 10 to the negative 3, and our original length was 1.5 metres. So you get 1.3 recurring, or 1.3 times 10 to the power of negative 3, and there's no unit because we're talking about strain. And then 3D, we are linking both those answers because we are talking about the Young's modulus, which is the stress divided by strain. So from the previous page, we're going to copy our answer of 6.6733 times 10 to the 7. That was the stress that we calculated, and we're dividing it by what we just worked out. The strain, 1.333 times 10 to the minus 3, and we'll get 5 times 10 to the 10 pascals. Question 4a is talking about some lengths of rail track which is pre-strained so that it stays in place when it changes in the weather. It's given us a couple of pieces of data, the Young's modulus, the amount of pre-strain is required for each Kelvin rise in temperature, but then it does tell us how much pre-strain is actually used in the end, 1.24 times 10 to the negative 4, and the tensile force required to make this. So I've written down the data and the equations we're going to need to work out the area. So we're going to work out the stress first, and then from the stress we can work out the area. So I'm going to rearrange my Young's modulus equation first. So stress is going to equal to our Young's modulus times by our strain. So we've got 2 times 10 to the power of 11 times by 1.24 times 10 to the negative 4. So our value for stress is 2.48 times 10 to the power of 7 pascals. Then with that we can use the second equation here, so we work out the area, and that's the force divided by stress. So our force is 0.19 times 10 to the 6, and we divide it by the stress we just worked out, 2.48 times 10 to the power of 7, and that should give us 7.7 times 10 to the power of negative 3, and that's in meters squared. Question 4b, the elastic strain energy is 4.2 kilojoules. So we've talked about elastic potential energy before. It's the same thing, or the work done. So I've written the equation for that, and we're going to rearrange that to find this extension, because what we're working out is the original unstressed length of the rail. So first, if I rearrange the extension, I'm going to get this energy, EPE, times 2 divided by F. So if we put some numbers in, we've got 4.2 kilojoules, that's 4,200 times 2 divided by our value for F, which we had up there is 0.19 times 10 to the power of 6. So the extension is 44.21 times 10 to the negative 3 meters. So that's 42 millimeters. We are then going to use the value of pre-strain to work out the original length. So if I rearrange this, it's our extension divided by our pre-strain. So 44.21 times 10 to the negative 3 divided by our pre-strain, which is 1.24 times 10 to the negative 4. And that's going to give us an original length of 356.53, or if we're rounding it to our two significant figures, 360 meters. Question 3c, calculate the temperature at which the steel rail becomes unstressed. So I found this quite a hard one to get my head around at the beginning, but it's not too bad. First thing we're going to do is we're going to ignore the temperature they've given us, even though I've just written that down as 6 degrees C, and we're just going to look at the pre-strains and the pre-strain per K. So we've been told what the pre-strain is, and we know how much happens per Kelvin. So that's a way of measuring temperature, just like degrees C. So to work out what the change in Kelvin is going to be between it being unstressed and having this pre-strain, all we're going to do is we're going to divide our pre-strain by the pre-strain per K, and that gives us 3.543 K. That is how many Kelvin it takes to change the temperature to make it that way of being pre-strained, or to change it back to being unstressed again. And then all we need to do is work out the final temperature. So when we're talking about Kelvin, although it's a different scale to degrees C, 1 Kelvin is equal to 1 degree C when we're talking about a temperature change. So our final temp, so it was 6 degrees before, but we've now added a change of roughly 3.5, so it's 9.5 degrees C. That is the temperature at which our rail becomes unstressed. Question 4D is asking us to state and explain whether the pre-strain was appropriate for all weather conditions. So overall, I'd say it's not suitable for the entire year round. That's because it's unstressed after only a very small temperature change of 3.5 degrees C or 3.5 Kelvin. And over the entire year, the temperature change is likely to be a bit more than this. So in the summer, there would be quite a large expansion of rails compared with this. Question 5 is talking about a rope climber, a mass of 70 with a rope of 2.3 metres and 1 centimetre diameter. And as he goes down, his gravitational energy is converted into elastic energy because the rope extends to 1.5 millimetres. So it says to ignore other kinds of energy like kinetic. So whatever he gains in gravitational potential energy, we're going to convert into elastic potential energy. So we'll start by working out his gravitational potential energy, or his change in gravitational potential energy, mg times the change in height. So his mass is 70, gravity is 9.81, and then for the change in height, it's going to be the length of the rope, 2.3, and that's before it's extended. And if we times them together, we get 1579.41 joules. All of that is going to be converted into our elastic potential energy, because the question tells us, which is half Fx is how it's written on your formula sheet. So that's half times the force times the extension. And we are working out the force, that's what the tension is. So we're going to have our answer from before, 1579.41 joules. And that's going to be equal to half times the force times the extension, which is 1.5 times 10 to the negative 3. So we are going to rearrange that for F. So what you type into your calculator is 2 times your answer from before, 1579.41. And we're going to divide it by our change in length, 1.5 times 10 to the negative 3. And the answer you're going to get for your force, for your tension, is 2.1 times 10 to the power of 6 newtons. Question 5b, we first need to calculate the stress in the rope. So stress is force divided by area. So our force is 2.1 times 10 to the power of 6. Then we've got to divide it by our area, which, if you remember, area is pi d squared over 4. So pi times 1 times 10 to the power of negative 2. That's all squared divided by 4. And you would put that answer underneath, because that's what your area is. And if you type that into your calculator, you get stress is equal to 2.7 times 10 to the power of 10. Or we could write that as 2.7 gigapascals. This one would just be in normal pascals. Then for 5c, we calculate the strain, which is the change in length divided by the length. So this is nice and easy. 1.5 times 10 to the negative 3 divided by our original length, 2.3. So you get 6.5 times 10 to the power of minus 4. And no unit, because we are working for strain. And finally, we're combining those to get our Young's modulus, stress divided by strain. So 2.7 times 10 to the power of 10 divided by 6.5 times 10 to the minus 4. And you should get a Young's modulus of 4.1 times 10 to the power of 13 pascals.